Okay, sir, go ahead.
Yeah. So today roadmap is discussion about multi-layer networks, feed-forward networks. We have two important aspects. That's why I allotted for those two entire for today and tomorrow. Feed-forward networks and feedback networks. To understand the feed-forward networks, first of all, you must learn backpropagation algorithm or backpropagation learning. So many students are asking applications. Yesterday also, many students asked applications, sir, please explain the applications. I think I am boring with the completely discussing the theory. So today I will give one or two applications also. Then I will go to backpropagation learning so that some interest they'll have some interest about the subject. So let us see the applications of neural networks in object recognition. So when an object is given to the system, that means webcam or something camera, it must be able to identify or an object or a face or anything. Neural networks let us discuss the neural networks, how these are used for complex vision systems in industrial and research applications. So object recognition systems. Vision-based industrial robots. So they are very helpful industrial robots. And today also, you can see in the newspapers, to help the corona patients, they are developing the robots. Robot is a machine, intelligent machine, which can walk. And chatbot is an intelligent machine which can chat or which can communicate, which can talk. Like that, many boats. It is not boat, B-O-A-T boat. It is not boat. It is boat, B-O-T boat. Boat means a machine, so which can communicate with the humans, which can recognize the humans, which can identify the humans. So chatbots are nothing but socially interactive robots. And similarly, autonomous flying vehicles. Today we are seeing drones. Drones are equipped with these object recognition or object identification machines. These boats, these drones will fly over a designated place, and they will identify, they will recognize, and they will send the information, object recognition. So it is necessary to recognize the shape of the patterns in image regardless of position, rotation, and scale. So when you go to image processing, if APSSDC allows, I can explain clearly about image processing applications and image processing basics also in another session, in another lecture. So it is necessary to recognize the shape irrespective of position, where they are, rotation, scaling. So and also let us take satellite images. Satellite will take image far away from the Earth. They will take the images of the objects on the Earth's surface. When you see these images, we can't understand. They are of different colors and different shapes. So this is another subject. study of satellite images and understanding, analyzing them. So how to distinguish the background and the foreground and the objects. And once the isolated objects can be extracted from the captured image, this is all entire thing. It is a research problem. So here for object recognition, they are using backpropagation learning, backpropagation learning. And two supervised, one is the supervised learning mechanism, we can also use unsupervised learning mechanism. So backpropagation algorithm is used for the position to identify the position, scale, rotation, and rotation invariant neural cost. So whatever the position of the image you have taken object, whatever the size, scale means size, rotation means in which angle it is there. All these can be robustly, you can extend with the help of neural networks using backpropagation. And similarly, unsupervised learning mechanism, coherent network, they can use coherent. They may be used to place similar objects into groups and also for edge enhancement. So this is all the research theory. You must study clearly why backpropagation can be used, what is the principle behind the backpropagation. So backpropagation is classified under the supervised learning paradigm. It is non-recurrent. Learning does not use any feedback information. That's why mostly it is used in feed-forward networks. So it is a supervised learning mechanism for multi-layered generalized feed-forward network. Actually, today's session, I must take the multi-layered feed-forward networks. Multi-layer networks, there is nothing but the feed-forward, which use backpropagation learning. But anyhow, I want to show some examples, some application. Then I will go to the theory, so that it will be better to understand. So this is a backpropagation is a supervised learning mechanism for multi-layered generalized feed-forward. So this is the backpropagation network. The inputs are there, and this is the hidden layer neurons. And we have many hidden layers. This is the nth layer, that is the output layer, and the output. Anyhow, the principle behind backpropagation feed-forward we will see in the later slides. Backpropagation is the most well-known and widely used among the current types of neural network systems. Can recognize patterns similar to those previously learned. So already we have given some training. If you give some training, if the network is able to learn some patterns, then definitely it will identify the similar patterns, the similar objects. So they are very robust and stable. But a majority of object pattern recognition applications use backpropagation networks. Backpropagation networks have a remarkable degree of fault tolerance for recognizing tasks. So that's why only most popularly backpropagation is used. They are very robust and also fault tolerant. So now the goal, the problem statement is object recognition by using neural networks. So processed photographs. Here processed photographs means pre-processing has been carried. Pre-processing means the noise and making a standard size of image, removing any, adjusting the contrast. There are many techniques in pre-processing. There may occur noise in images, so you must remove the noise. And similarly, contrast may be non-uniform, it must be adjusted. And if possible, we can segment the image. All these comes under processing of 14 household objects under various orientations. Orientation means angle. Were considered for training pattern. They are considered for the network training pattern. Images were captured and pre-processed to extract object future data. So what I told, they are captured from ordinary digital camera. And they are pre-processed. Pre-processing, as I told you, noise elimination, contrast adjustment, etc. And the size also it is made standard. To extract the object future data. And now the backpropagation network is trained with 9 patterns. We have taken 14 patterns. Among them, 9 patterns are used for training. And remaining 5 patterns are used for testing. See, this is a total of 14 objects to be classified into 5 groups. Some of the objects are in rectangular shape. Some of the objects are in circular shape. Some of the objects are square. Some of the objects are triangular. Some of the objects are cylindrical. You can observe here ball and this shooting board. They are all circular shape. Books and wall hangings and weight measurement disc. They are all in rectangular shape. And cocoa bottle, cocoa tin, and some other items are in cylinder shape, and also some triangular shape also. Now we will give these objects in different angles, even though they have rotated into different angles. They must be classified into 5 groups. So see here, rotation also. Rotation. It is 0 degrees rotation. It is rotated with an angle. This is offset means 0 degrees rotation only, but it is displaced from its current position. It is displaced from current position. So variance in position, this is the variance in position. And rotation, of course, scaling means magnitude. It is not shown here. So all these must be, the algorithm developed must be invariant to all these. Invariant to position, invariant to rotation, invariant to scaling. So this is a cereal box. Some, I think, chocolates or something box. So it is pre-processed to give the network engine. It is inclined by 45 degrees. This pre-processing and is everything is done by image processing techniques. Now we have a toolbox, neural network toolbox. They have taken toolbox. The object is, the input object is rectangle. It is named as rectangle tool. Cereal box. Its position of incline is 45 degrees. We can also select the position also. And slowly we are incrementing the angle 10 degrees. 10 degrees. So the inputs to the network were normalized radius values measured from the centroid of the object to the edge of the object in increments of 10 degrees. So initially we will measure the centroid of the object and to the edge of the object. Then we can know the angle and the angle is incremented 10 degrees here. Radius versus theta. And this is normalized radius versus theta. So these are the max angle of maximum for 355 degrees. This toolbox can be developed by anybody if you use simple image of some any language. You can easily simply develop this toolbox. And it is very easy to use for any object. So when we are shifting slowly the angle 10 degrees, 36 data point, and 30 degrees, 18 data points, 60 degrees, 6 data points, and 90 degrees, 4 data points. So analysis of training data for training set. Similarly, we are giving the book rotated angles, rectangle, and scales, square, triangle, cylinder, circle, softball, rotated angle, all these are given. We can select any one of the objects from each category for training. So 9 selections are made to be made for training the 9 output neurons. One object from each group at 0 degrees, 5 total. One object from non-circular groups at 40. So with a different angle, different objects we are giving for training. Now we are running the neural network. We are training the neural network with back propagation with momentum. Here there are neurons in hidden layer 85. Neurons in the hidden layer. We have number of neurons in hidden layer 85. And learning rate is set 0.3. And momentum coefficient is set 0.7. And the acceptable error is only 5%. And also we can train by incrementing the angle, by rotating the book. So when you are rotating the slowly object, the neural network will learn the shape of the book and the rotation of the book and the position of the book. So training is made. See here, elapsed time, total time is 2478 seconds. In good olden days, it will take more time. Today it may be very milliseconds only. i7, 10th generation, high speed, multi-core systems are available today. I have done my research work on, even I think it is not Pentium also. So when I program it, when I give the input data and train it, normally I use it to sit at 10 o'clock in the night. I don't want to disturb anybody in my house for my experiments. So when I sit at 10 o'clock, the output has occurred after 2 hours or 3 hours at midnight, 12 o'clock, 1 o'clock. So training epo by epo, continuously it rotates cycle by cycle. And ultimately, that is a good old machines before Pentium. I don't remember the configuration. Today, we have many powerful machines. Today we have. So the elapsed time will be also in the range of milliseconds. And here the number of iterations are 591 and the average error is at 5%. So after the training, the user may test all 36 configurations based on the results of the 9 training configurations. We can change the test object. We can change the angle and orientation, position. Now the network is able to recognize it is a rectangle. So even though this front end is not needed, of course, front end is not needed. For a layman to understand, front end is needed. So this is the object recognition from digital image, entire this one. So we can select an object, we can select the angle, the position, and we can change the increment of angle, 10 degrees, and number of neurons, learning rate. We can change them, and we can train. And similarly, now this is the testing module. Then the output response is it is a rectangle. So this is the nothing but graphical user interface. There is no need of graphical user interface when you are doing research. Simply it is some BTech project or MTech project. Now we must learn the concept. There is no need to worry about the front end graphical user interface. When you are doing a project at the BTech level or MTech level, if it is the front end, it is okay. But when you are doing research, our main concentration is on the how the rotation, angle, position, there are feed to the network, and here feed forward network is a back propagation algorithm. So what is happening here in the back propagation algorithm? So now the network is successfully able to classify the objects. So average time is 42 minutes for 100% accuracy. The time, don't worry about the time. The time depends upon the machine. Today still lesser time is occurring, and number of iterations are 552. So when the network was trained to within 2% error, the time was 3 hours. See here, 3 hours. And 2493 iterations. So if you want better accuracy, it takes more time and number of iterations also more. So the principle behind this type of recognition is backpropagation algorithm. So you must go for this backpropagation algorithm. Today, let us learn about this backpropagation algorithm. And then if the time allows, we'll see another 1 or 2 applications. So feed-forward network of at least one layer of non-linear hidden nodes of layers L is greater than or equal to, not counting the input layer. So we are going to take feed-forward network of at least one layer of non-linear hidden nodes of layers L is greater than or equal to, not counting the input layer. So normally, if it is not a deep learning, if it is a general learning method, 1 or 2 hidden layers are sufficient. Only 1 or 2 layers are needed. If it is a deep learning, we will go for more than 2 hidden layers. Yeah. So the most activation function here is sigmoid function. So S of net output is equal to 1 by 1 plus e to the power of minus. So learning here is supervised. Already told in the previous slide also. The learning here we are using is supervised, and it is error driven generalized delta rule. It is the error driven generalized delta rule. So this type of networks are called as backpropagation networks. We can call these feed forward networks also backpropagation nets. So here weight update rule is gradient descent approach. You must recollect all these things. I explained what is delta rule, what is supervised learning, what is error driven learning, what is sigmoid function, and what is gradient descent approaches. Gradient descent minimization approach. So if we are good at all these, which we have discussed in the previous sessions, then it is very easy to understand this backpropagation learning. So weights, two matrices, the one matrix of weight, already we have seen in the last session. Weights can be given in the form of matrix. Everything, the mathematics behind this neural network is nothing but the matrices. Inputs can be given as vectors. Matrices can be, weights can be created like a matrix. And output is again a vector. So W10 from input layer 0 to hidden layer 1, all these, this is a vector of matrices or matrix. Is a matrix. W10, 0 is the input layer 0 and 1 is the hidden layer. W21, it is the from hidden layer 1 to output layer 2. As I told, there is only one hidden layer here. Only one hidden layer here. And W2, 1 of 10 weight from node 1 at layer 0 to node 2 in layer 1. So you please understand the notation. The above, whatever the uppercase, it shows layer, and the lowercase shows the nodes. Node 1 in the layer 0 is connected to the node 2 in the layer 1, and its weight is W2, 1 of 1, 0. And the training samples a pair of XP and DP. Since it is a supervised learning, in supervised learning, we must give the desired output also. So input pattern, it is a vector XP, 1, XP, 2, XP, 2, so on. Output band, corresponding output patterns, we'll get the output patterns. And similarly, we must know the desired output patterns. And therefore, error is equal to output minus desired or desired minus output. And the sum of the square error. Squared error is nothing but sigma of sigma error square. So this error is used to change the weights 1, 0 and 2, 1. 1, 0 means weights between the input layer and hidden layer. 2, 1 means weights between the hidden layer and the output. I think you are clear with the notations. So weights are two weight matrices. We are going to create weight matrices. One is for input layer to hidden layer, and another is for hidden layer to output layer. And we are training now the network with input patterns, X and input patterns. And we'll get the output response, corresponding output response. And also we are giving it, since it is a supervised learning, we are also giving desired output. And we are going to calculate, and we are making squared error. This squared error is used for deciding the change in weights. And here we are using, as I said in the previous slide, sigmoid function. when we differentiate the sigmoid function, so I can write it as s dash of x. That means differentiation of sigmoid function, s of x into 1 minus s of x. See here, it is similar to the step function only. If you use step function, as we said, it is a perceptron learning. The only difference is in step function we have sudden change, that is only to access binary activation 0 or 1. Whereas here it is a smooth change. Smooth change. It allows number of variations. So when the response of the net is sufficiently large, it moves into one of the two saturation regions, behaving like a ramp function. And we have chain rule of differentiation. All of you know chain rule of differentiation. If z is equal to f of y is equal to g of x is equal to h of t, then dz by dt is equal to dz by dy into dy by dx into dx by dy. Therefore, this is nothing but f dash y into g dash of x into h dash of t. This is a simple equation everybody knows at the intermediate level. Now, let us see how we are going to forward computing. Apply an input vector x to input nodes. So, in the case of previous example, we are giving the features of the book, rectangular book to the network. Whatever may be, angular, shape, or size, or whatever, position. So, we are giving the input vector. And we are computing the output vector on hidden layer. So, you must compute from input to hidden and hidden to output. X j of 1, that is the output of hidden layer, is the sigmoid of net output of jth node at the hidden layer. This is equal to S of sigmoid of again sigma of wj comma I of 1 comma 0. 1 comma 0 means input to hidden layer, 0 to 1. 0 to 1 is into xi. It is very clear. Ji represents nodes. Node in the input layer and node in the corresponding node in the hidden layer. I is the node in the input layer and j is the node in the hidden layer. Now we are computing the output of the network. This is the again sigmoid of net output of the second layer of kth node. You observe the architecture of feed-forward network. We have input layer. That means I number of inputs are there. Hidden layer, j number of outputs, j number of neurons are there. And output layer, k number of neurons are there. W01. 01 means 0 is the input layer, 1 is the hidden layer. 1 comma 1, W1 comma 1 means first node in the input layer to the first node in the hidden layer. 2 comma 3 is the third node in the input layer to the second node in the hidden layer. Be aware of these notations. Then it is very clear. If the notations are clear, the architecture is also. Now, we want to, the objective of this learning, this training is to reduce the error. The objective of the learning is to reduce the error. The error is nothing but, as we seen, sigma of error square. For a given training samples, as much as possible. If it is possible, we must reduce to 0. Or if it takes more time, if it takes more time, let us reduce as possible as the error. So what is the idea now? What is the idea behind backpropagation learning? Update of weights in W21. W21 means hidden layer to output layer using delta rule as in a single layer net using the squared error. So we have discussed yesterday delta rule, delta learning rule. So by using the delta learning rule, we are going to update the weights. That's why we will calculate the squared error. Delta rule is not applicable to updating weights W10. You observe this point is very important. We are only using delta rule to update the weights between the hidden layer and the output layer, but not the input layer and hidden layer. So why we are not using here delta rule for the input hidden layer is we don't know the values of hidden layer. We know only the error at the output. We don't know what are the values we will get at the hidden layer. That's why propagation errors at the output nodes down to hidden nodes. These computed errors or hidden node drives the output update of weights W10 again by delta. So as we don't know the output of the hidden layers, we are propagating errors at the output nodes to hidden nodes. That means to hidden layer. These computed errors are hidden nodes. So again we are calculating the computed errors at the hidden nodes are used to change the weights. Again by using delta rule. That's why this learning is called error backpropagation learning. We are taking back the error at the output to the hidden layers. Or we are computing the errors or hidden nodes. So now how to compute errors or hidden nodes? This is very, very important. Error propagation can be continued downward if the net has more than one hidden line. The same procedure can be used if there are more number of hidden layers. So this was proposed first by Verbose, 1974. And in 1986, Rumelhart and Hinter and Williams have formulated how to calculate the errors at the hidden layers. I think it is clear why the name backpropagation was taken. Actually, we are calculating the output error at the output layer and taking the square of the error. We are using delta rule to change the weight between hidden layer and output layer. And the same must be happened at the hidden neurons or hidden layers also, but we don't know the response of the hidden layer, just we are calculating the response at the output layer. That's why now we are propagating the errors to output node down to hidden nodes and we are computing the errors at the hidden nodes also. So now the problem is how to compute the errors at the hidden layer. So all of you know the generalized delta rule we have discussed in the yesterday's session. For a given sample, we are going to calculate the energy. Whatever you say energy, squared error, nothing but. So updation of this weights by gradient descent algorithm. Our weight W21, that means hidden layer to output layer. Delta K comma J. K comma J means nodes. Kth node in the hidden layer to the kth node in the output is proportional to minus dou E by dou W. And similarly for weight W1 comma 0, delta W1 comma 0 is proportional to minus dou E by dou W. It is a simple derivation. Since this energy or error is a function of desired response minus output response, and similarly desired response minus output response is a function of net of 2. Net of 2 means the output layer. And again net of 2 is a function of W2 comma 1 by chain rule, as we discussed the chain rule there. It's the chain rule. Dou Z by dou T. That's why only I explained. I am explaining simple mathematics also to understand these algorithms and the equations. Dou Z by dou T is dou Z by dou Y into dou Y by dou X into dou X. So by the chain rule, dou E by dou W can be written as dou E by dou error. Dou error means desired response minus output. Again, this can be written as dou D minus dou by dou net of 2, dou net of 2. Again, dou net of 2 by dou W of 2. So we can cancel these two, and ultimately we get dou W by dou E by dou W. So this is equal to minus 2 D minus O, desired response minus output error, and S dash of net 2 into Xj. S dash means sigmoid function. It's a derivation. We have seen S dash is equal to S into 1 minus S. Sigmoid also. S of X, S dash of X is equal to S of X into 1 minus S of X. Now derivation update rule for W1 comma 0. So consider a hidden node J. Let us consider hidden node J. Weight Wji of 1 comma 0 influences net of 1, definitely. Net of 1 means the response at the hidden layer. The response at the hidden layer. This is the output. The weights are W2 comma 1. This is the hidden layer, the weight of 1 comma 0. Connection between ith node to jth node in the hidden layer, that is W. So it sends S of net 1 to all output nodes. So here S of net 1 is calculated and sent to all the output nodes. All k terms in E are functions of W1 comma 0. That is also true. So error function or energy, whatever may be, is equal to sigma D minus O of whole square. Whereas output is S of net 2. And net 2 is equal to sigma of X into W. And X of 1 is equal to S of net 1 into S of net 1. S of net. X of 1 means output at the hidden layer. Sigmoid of net of 1. And net of 1 is equal to sigma of Xi into W1 comma 0. So you slowly understand. It's very easy. There is nothing to be afraid, or it is not a difficult equation. Simply just let us say prefixes and suffixes, and this will confuse. Don't worry about k, j, something. Here we have error. It is squared. D minus O, D is meant desired output, and O is the actual output. We are taking whole square, error square. And output, final output, we have net 2. Net 2 means what we are responding, and sigmoid function we are using, activation function. That's why S of net 2. And net2 is nothing but the sum of inputs and to weights. So sum of the inputs at the hidden layer, that is x of 1, into its corresponding weight, w of 2 comma. A and J are the corresponding nodes in the hidden layer and the output. And similarly, x of 1 is nothing but s of net 1. And similarly, net 1 is equal to x into w. And now dou E by dou output is equal to dou S of net 2 by dou net of 2. So, see this chain rule. Chain. Dou net of 2 by dou x of 1, dou x of 1 by dou net of 1, dou net of 1 by dou w. Now, ultimately, dou E by dou weight. Dou E by dou weight is equal to sigma of minus 2 into error d minus o into s dash of net 2. S dash of dou s means s dash net 2 into weight w2 comma 1. Again into s dash of net 1 into xi. So this is very clear. Now the update rules for output layer w21 output layer. Dou E by dou w2 comma 1 is equal to minus 2 into d minus o into s dash of net 2 into x of 1. X of 1 means output response of hidden layer or input response of output layer. Input response of output layer is nothing but the output response of hidden layer. And change in the w2 comma 1. Change in the w2 comma 1 is equal to neta is the learning rate, all of you know. Neta into delta k into xj, where delta k is equal to dk minus OK, desired response minus output response into s dash of net 2. S dash of net 2. So for inner layer weights, W of 1 comma 0. For inner layer weights, W of 1 comma 0. That means from input layer to hidden layer. Dou E by dou W 1 comma 0. That is equal to sigma of minus 2 dk minus OK into S dash of net of 2. W2 minus 1 2 comma 1 S dash of net of 1 into xi. Therefore, delta W of 1 comma 0 is equal to neta into mu into xi, where mu is equal to sigma of del we have shown there, d minus o into s dash of net 2 into W of 2 comma 1 s dash of net of 1. So weighted sum of errors from output layer. So that's why, as we said in the earlier slides, the output error is propagated to hidden layers to calculate the error at the hidden layers. That's why the name came back propagation. The change in the weights depends upon the error at the output also. Change in the weights regarding the hidden layers depends on the error also. Error at the output. The weighted sum of errors from the output. And now let us see the algorithm. Start with randomly chosen weights. So design a network, design a feed forward network. As we shown, number of input neurons and one hidden layer with hidden neurons and output layer. So choose randomly weights while mean square array is unsatisfactory. and also computational bounds are not exceeded. So do all these things. For each input pattern, P is the input pattern. Number of patterns will give for trying. Compute hidden node outputs, net of 1. Hidden node inputs, net of 1. Compute hidden node outputs, x of 1. Compute inputs to the output nodes, net of 2. Compute final outputs, O. Modify output outer layer weights with delta W of 2, 1 is equal to eta into D minus O, S dash of net of 2 into x of 1. And modify the weights between the input and hidden nodes as delta W1, 0, eta into sigma of D minus 0 into S dash of net 2 into W of 2, 1 into S dash of net of 1 into X I. So already we have shown S dash of X is equal to S of X equal to X. So it was clear. I think I had made clear the algorithm. Why the name backpropagation came? Feed forward with the backpropagation. Don't be misled. It is not a feedback network. It is not a feedback neural network. It is a feed forward network with errors back propagating. With errors back propagating. So now how the pattern classification is performed. How we have performed the pattern classification. Two classes, one output node. If there are two classes, one output node is sufficient. Whether to say 0 or 1, yes or no, whether it belongs to particular class or not. If n classes, log n output nodes, binary encoding. Binary encoding. If 8 classes are there, 3 outputs are sufficient. 2 cube is equal to 8, no? So better using n output nodes, a class is represented as 0, 0, 0, 0, 1, 0. And we are using a sigmoid function. Nodes at output layer will never be 1 or 0. But either 1 minus E or error. So don't be confused. Here we are not getting 0 or 1. Yes, we must assume yes or no. Yes or no depends upon error. If error is less, it is yes. If error is more, it is no. So neural network cannot show, it cannot display that 0 or 1, or it cannot say yes or no, or true or false. It simply gives the response. Response is nothing but the error. Based upon error only, we must say whether it is true or false. Of course, if you want, you can create another encoder to convert error into 1 or 0 using a threshold parameter. Error reduction becomes slower when moving into saturation region. So as we see in the sigmoid function, as we have seen in the sigmoid function. So error reduction will be less when we move to the saturation. When we move to the saturation, as we are using the sigmoid function. So for fast learning, for a given error bound, set error is equal to output plus 0, initially 0. If D minus O is less than or equal to error. When classifying an input X using a trained BPNet, classify to kth class if dk is greater than dl. Dk means desired response of the kth node, and dl is the desired response. So that is the classification. We will get response. As I given the example of initial day before yesterday or something, I have shown how the neural network is going to identify the character recognition and written recognition. Two I have shown two. We have numerical values, 10 numerical values. So if it recognition means it shows the response, high response at that particular output. So based upon the response, the desired response or output which has that output response, we will classify it into that category. So another example is classification of myoelectrical signals. In input pattern, we have three futures normalized to real values between 0 and 1. So here this is also normalization. Normalization and conversion is very, very important. Neural network will take only input as numerical values only, whether it may be fractions or integers. Since we are doing a mathematical calculation inside the neuron, a neural network is nothing but a calculating machine, mathematical calculating machine. So as we are calculating mathematical, you must give the numbers, whether it may be the fractions or integers. So one thing is we must convert, even though we have any words or something into numericals. And also if they are large values, they must be normalized. And output patterns have two classes, success or fail. And network structure is 253. 253 means 3 input nodes, 2 output nodes, and 5 nodes in hidden layer. And learning rate neta is the 0.95, momentum is 0.4, error bound is 0.05. That means whenever the error reaches 0.05, it will stop. And he has given 332 training examples. The maximum number of iteration set is 20,000. So it was stopped. Even 38 patterns remain misclassified. So this is the output of this example. Iterations, iteration by iteration. Fraction of samples misclassified. How many number of samples are misclassified? And also mean square. Here array is going to be saturation. Slowly array is going to be saturation. At 20,000 almost all error is here. And also samples misclassification also same. Then we can stop. It is not possible to achieve zero error. We have kept the bound also 0.05. So actual class in which network places sample 1, 2, 3. Desired target class 1, class 2, class 3. So 38 patterns are misclassified. In the class 1, 5 are misplaced. In class 2, 3 and 9 are misplaced. And class 3, 2 and 19 are misplaced. Total 38 patterns are misclassified. So for the given W is equal to, we have two weight matrices, W1 and W2 comma. And output is equal to fx. So we can convert it to a function. Theoretically, feed-forward nets with at least one hidden layer of nonlinear nodes are able to approximate any L2 functions. It's all squared integral functions, including almost all commonly used math functions, to any degree of accuracy. provided there are sufficient many hidden nodes. So an L2 function in mathematics can be approximated by Fourier series. The mean square error converges when n tends to infinity. Of course, this is not needed more. If you are dealing with the digital signal processing, then we must go for this. At present, we are not going to discuss this. The strength of BP learning is great representation power. Many functions can be represented. BP learning gradient descent approach. Wide applicability. It only requires that good set of training samples. Does not require any prior knowledge. This is one advantage. Our deep understanding are also deep understanding. Easy to implement the core of learning algorithm. Good generalization power. And definitely at the same time it has limitations also. Learning takes a long time to convert. That's why I used momentum there. Even the momentum used it has taken 20,000 iterations. The previous example we have seen. The momentum is 0.4 or something we have given, even 20,000. So net is essentially a black box. It may provide a desired mapping between input and output, but does not have information of why a particular X is mapped to a particular output. The mapping is there, definitely mapping is there. But what type of mapping we are unable to explain. So that's why it cannot provide explanation. This is because hidden nodes and learned weights do not have clear semantics. So how many hidden nodes must be there? We don't have a clear semantics. Unlike many statistical methods, there is no theoretical well-founded way to assess the quality of BP. So what is the confidence level one can have for trained BP net with final error? What is the confidence level of output computed from input X using such? So still is yes, some limitation definitely. If it is not clear about the hidden layers and hidden weights, it still looks like a black box. But it is used in many applications. And also here you are using gradient descent algorithm, gradient descent learning. Only guarantees reduce the total error to local minimum. That I discussed also in previous sessions. This gradient descent learning definitely reduced to local minimum only, but not the global minimum. So whenever the network will fall to local minima, it's stuck there only. That's why I used momentum. And also it depends upon the shape of the error surface. Too many wells will make it easy to be trapped into local minima. So error surface must be smooth. If the error surface is smooth, then definitely it will work very efficient. If the error surface has too many valleys, we have shown in yesterday's session, it is stuck in the local minimum. So that's why to overcome these remedies, try the same net with different hidden layers, different number of hidden layers, different number of hidden nodes. So therefore, they result the different error surfaces. We can select the better error surface. And also with the different initial weights, that means different starting points. Just you take an example. We are searching a treasure hunt. We are searching a treasure hunt. We don't know where the treasure is. We are moving in a dense forest. This forest have mountains and also valleys. What is the correct path? We don't know. So where we are starting, it is also a matter. So if you change the starting point, that means the weights. Sometimes we fall into valleys, and sometimes we can go straight. So for forced escape from local minima by random perturbation, simulating anything or using momentum. So as this is the problem in the back propagation, we can guarantee we cannot guarantee generalization. Even if the error is reduced to zero, it may not be able to select the new sample. And also here we have another problem, over training problem or overfitting. So we have trained it with a number of samples and the error is zero, even though the net is unable to give accurate outputs for input which are not in the training. That's why you must give more and better samples. And as possible as try to use this small net and using larger error bound so that it will be terminated early. Introducing noise into samples. So if you introduce the noise into samples, definitely it will adjust itself and it is also ready to recognize the new training, new sample. And also cross validation. Leave some of the samples as test data and periodically check error on the test data. Learning stops when error on test data starts increasing. So this is cross validation. That means time to time has to validate the network, whether the network is working properly. We are using here activation function sigmoid. So it reaches the when it reaches this saturation, then we call it as network paralysis. So there are two saturation regions we have. So it's a derivative s dash of x tends to 0 when x tends to 0. Either side. When x falls, a saturation region, s of x hardly changes its value, regardless how fast the magnitude of x increases. So input to a node may fall into saturation when sometimes some of its incoming weights become very large during learning. So this is called as network paralysis. It is obvious. We have seen in the example also. When it going to saturation, this classification rate is not changing, error is also not changing. So to overcome this, use non-saturation activation and also periodically normalize all the weights. The learning accuracy, speed generally is highly dependent on set of learning parameters. Initial weight, learning rate, momentum, number of hidden layers, number of nodes. So these are all determined empirically by experiments. We don't know initial. Nobody knows initially what are the initial parameters. So we must find out them empirically. And coming to practical considerations, if you do experiments, a good backpropagation requires more than the core of learning algorithms. Many parameters must be carefully selected. So they must be selected carefully. So parameters must be carefully selected. Although the deficiency of backpropagation nets cannot be completely cured, some of them can be easily by using some practical values. So initial values weights and bias randomly selected. I have shown the ranges also. -0.05 to 0.5. And normalized weights for hidden layers. Random assign initial weights for all hidden nodes. For each hidden node, normalize its weight by the given formula. And also number of hidden nodes and number of hidden input nodes. And avoid the bias in weight initialization. Quality and quantity for training samples often determines the quality of learning results. Samples must collectively represents well the problem space, random sampling, proportional sampling. And number of trained patterns needed. Theoretically, we don't know. It depends upon the application. For example, we have total number of weights is 27 and error bound is 0.05 and number of patterns is 540. We can successfully train the network to correct classify 526 of the samples. That means the network will work with 95% performance. So how many hidden layers and hidden nodes per layer? This is also very, very important. In practical rule of thumb, if n is the number of input nodes, m is the number of hidden nodes. For binary or bipolar data, normally m is equal to n. And for real data, m is greater than 2n. Multiple hidden layers with fewer nodes may be trained faster for similar quality in some applications. Don't make the net as fat and thick with more number of nodes. It must be thin and long. Thin and long means more number of hidden layers and less number of hidden nodes. The network must be thin and long, but not be fat and short. So as in the human life, thin and tall person can walk and run with fast, whereas thick and fat and short, he can't move. The same way here also, with less number of hidden layers and more number of hidden nodes, the network cannot be able to when compared with the thin and long. And similarly, data representation, binary versus bipolar. Bipolar represented use training samples more efficiently. Binary means 0 and 1, bipolar minus 1 and 1. Better to use bipolar. There has no learning occur when there is 0. When the input is 0. When it is bipolar, then again learning will be there. And number of patterns can be represented with an input nodes. Binary 2 to the power of n patterns and bipolar 2 to the power n minus 1 if no bias is used. And similarly, it is real value data, input nodes, real value nodes, and they must be normalized as I shown, they may be normalized. And hidden nodes are sigmoid. Node functions for output nodes often linear. Training may be much slower than with binary bipolar. So when compared to bipolar inputs, when real world data, training will be slow, definitely. These are all practical considerations. These are all practical considerations. One must be careful about all these practical considerations when you are implementing practically for any application, pattern recognition. And similarly, adding the momentum. Already I have shown how the helps to speed up learning. We are using momentum term also. Theta is the learning and alpha is the momentum. It is an exponential sum of all previous updates. It gives. But you must avoid sudden directions of weight update. And similarly, batch mode of weight updates. Weight updates must be carried once per each epoch. Must update weight at each epoch. Smoothing the training sample outliers, learning independent of the order of sample presentation, usually slower than in sequential. And variation of learning rate, fixed rate much smaller than the one. Start with large n, gradually decrease its value. Start with a small n, steadily double it until mean square start to increase. Give known underrepresentation samples higher rates. Find a maximum safe step size at each stage of learning. And adaptive learning rate, delta bar method. Each weight has its own learning rate. Each change in the weight remains in the same direction, increase in eta. If it changes the direction, decrease in eta. This is all obvious, but I am explaining again. When you are going to implement, you remember all these points. So, for example, experimental comparison training for XR problem, batch mode. 25 simulations with random initial weights. Success if E is average over 50 consecutive hours. Less than 0.0 results. See here, method. Only simple backpropagation, simulation 25, success are 25. And epos are, mean epos are 16,000. With momentum, 25, 25. And epos are 2,000. With the delta, bar delta, 25, success is 22. And number of epos are 447. So you must decide what percentage of error must be there, what time must be. And for quick propagation, E is parabolate shape. E does not change sign from t minus 1 to t. You observe here t minus 1. So W of t plus 1 into W of t into E dash of t into W of t minus 1 by E dash of t minus 1. E dash of t. This is parabolate approximation. So we can use other node functions also. Not only sigmoid function, you can use bipolar sigmoid function. The only thing is to change the slope of the logistic function. That means larger slope means quicker to move to saturation region. That means faster convergence. Smaller slope means to move very slow to move saturation region. Allows refined weight adjustment. So better to go for smaller slope. So if you use for each node a different slope, that is adaptive. So many works are there on neural networks. Without knowing all these things, they are implementing and using even in the PhD also. It is very funny and also very sad. So another sigmoid function with slower saturation speed. F of x is equal to 2 by pi arc tan of x. This has this saturation. And similarly, some of the functions are non-saturating functions. Log of 1 plus x and minus log of 1 minus x. You can select any function which does not go into saturation or slowly goes to saturation. So applications, learning XR, initial weights. You try it. This is a very simple example you can try. Even you can try in the book also. There is no need of going for a computer or some machine. Simply you can work on the book with a pen and paper. So you take random weights minus 0.5 and 0.5. We have two inputs only. That's why minus 0.1. Hidden nodes, single layer of 4 nodes. As I told, 2, 4, 1. Two inputs, 4 outputs. Two input nodes, as we seen there, number of nodes in hidden layer are double that of input nodes. 4 hidden nodes and 1 output. And we can use bias. And learning rate is we have kept a 0.02. Variations tested, binary versus bipolar representation. And different stop criteria. Normalizing initial weights. Bipolar is faster than the binary. You can use -1 and 1. Don't use 0 and 1. You assume 0 as -1. So convergence 3000 epos for binary, whereas 400 epos for bipolar. It takes 400 epos. You try on the book for 4 or 5 epos, then you come to know what is happening in the book. Then you can give on the machine. So binary nodes and bipolar nodes, see the convergence. Binary nodes are converging at 3000 epos, bipolar nodes are at 300 or 200. So relaxing acceptable error range may speed up convergence, plus or minus 1.0 is an asymptotic limits of sigma. When an output approaches plus or minus 1.0, it falls in a saturation. And similarly, you can use plus or minus A also, where A is between 0 to 1. We can set the saturation. So normalizing initial weights may also help. So binary, randomly if you take weights, it is 2800 epos. Whereas if you take normalized weights, 1900. Similarly, bipolar 387, it is 224. Bipolar setting the target 0.8, 264 and 100. This is all practically to optimize the network. So yesterday somebody asked how the data compression is made, image compression or data compression, whatever may be. Yesterday somebody asked the question. So it is auto association of patterns with themselves using a small number of hidden nodes. So we have input vector, hidden nodes M and output nodes. If training is successful, applying any vector X on input nodes will generate the same X on output nodes. Pattern Z on hidden layer becomes a compressed representation of X, a smaller dimension. So its main use is reducing the transmission cost. So how the data compression is made is, hidden layer becomes a compressed representation of X, a smaller dimension. M is less than N. You can reduce the number of hidden nodes. See here, N, M, N. Normally we are taking 2, 4, 1. In the previous example, we are taking 2, 4, 1. 2 input nodes, 4 hidden nodes, 1 output node. In the previous example. XOR operation for XOR. Here we are taking N, M, N. N, M, N. N is the input number of nodes in input. And M is the number of hidden nodes which are less than the input nodes. And similarly, N is the output nodes. We are getting the same output, but it was compressed. How it is compressed means we are using less number of hidden nodes. That means whatever the unnecessary data will be removed at the hidden nodes. So compressing character bitmaps. You can go for character bitmaps. Each character is represented by a 7 by 9 pixel bitmap. 3 into 3, 9 pixel bitmap. Or a binary vector of dimension 63. 10 characters A to Z are used in this experiment. This is also a small experiment you can do as a project for BTech students. So error range, given tight and less also, loose also. And relation between number of hidden nodes, error range and convergence range. Relaxing error range may speed up. Increasing the number of hidden nodes may speed up. These are all we have given the practical applications. error range 0.1, hidden nodes 10, number of epochs 400, error range 0.2, hidden nodes 10, epochs 200 plus. So still more other applications, medical diagnosis, input is symptoms, lab tests, etc. Output possible diseases. Nowadays, many expert systems are there, and also many people are doing experiments on this also. Problem: no causal relations can be established. Hard to determine what should be included as inputs. So currently, focus on more restricted diagnostics. Predict post-stage cancer or hepatitis B based on standard blood tests. So input environment parameters, output control parameters. And similarly, stock market forecasting, input financial factors, output forecasting of stock prices. Consumer credit application, credit evaluation, based upon the loans he has taken and repayment, etc. You can go for credit evaluation. I think we don't know. Some CRISIL rating will be given. A plus plus or A plus plus, A something. This CRISIL rating is depends upon the personal financial information, how much income is coming, how many loans are there, how he is paying the installments, etc. That is, the output is credit rating. And it is key for successful application. Careful design of input vector. The input vector is very, very important for your application. The features you have selected. How the features you have selected. You must obtain the good training samples. So, coming to summary, backpropagation networks are nothing but multi-layer feed forward, full connection between nodes in adjacent layers. Already we have stated in the initial classes only. Feed forward means connection between the adjacent nodes, adjacent layers. No connection within a layer. No connection. One or more hidden layers with non-linear activation function. Most commonly used sigmoid. One or more. More means only two. If you go for more hidden layers, it will become deep learning. And is a supervised learning. And approach is gradient descent to reduce the total error. Error terms at the output nodes are calculated. They are propagated to the hidden node to calculate the error terms in the hidden nodes. And to speed up the learning process, we have added momentum and adaptive learning also. And also generalization is based by cross validation. Time to time we are going for cross validation. Strength of backpropagation is great representation power, wide practical applicability, easy to good generation. Most of the application you are used by this backpropagation. And problems are learning often takes long time. The net is essentially a black box. Gradient descent approach only guarantees a local. Every function cannot be represented. We cannot guarantee generalization. And network paralysis may. So all this must be avoided, as I shown practical considerations. I shown the practical.
Sir, PPT आगे sir.
No, yeah. I'm changing the PPT. I'm showing some applications. That's why I'm changing.
Okay.
Now let us see some more applications, some more practical applications. Some more case studies. Yesterday, many students asked the case. They can implement the project. So I think you are clear about the backpropagation feed-forward networks. You can use this feed-forward, backpropagation feed-forward. According to my experience and my knowledge and also my notes, I have written all the practical consideration. Or otherwise, you can go for the textbook also. If you have any doubt, you can verify. The first one is the character recognition using neural networks. Character recognition for the neural networks. Both printed and handwritten characters is a typical domain where neural networks have been successful. And also we can use for optical character system for among first commercial applications. Today everybody using optical character recognition for examinations, for entrance examinations, this one, NET, JEE, mains, MSET, everything. They are all optical character recognition. Bubbling. So let us demonstrate an application of multi-layer feed-forward network for printed character recognition. For simplicity, we can limit our task to the recognition of digits from 0 to 9. Now, it can be extended to any character, whether it is A to Z or something. But it is very, very difficult to implement for Telugu characters. The simple characters are English only, A to Z. And recognizing Telugu characters is very, very difficult. It has 4 levels. తెలుగు అక్షరాలు ఇంగ్లీష్ అక్షరాలు చూసినట్లయితే మనకి ఏమి ఒత్తులు గిత్తులు దీర్ఘాలు ఏమి ఉండవు. జస్ట్ సింపుల్ లెటర్స్ ఓన్లీ ఏబిసిడి. అలాగే ఎక్కువగా దే ఆర్ మేడప్ ఆఫ్ స్ట్రైట్ లైన్స్, వర్టికల్ లైన్స్, సర్కిల్స్ అండ్ సెమీ సర్కిల్స్. ఏ అన్నాం అనుకోండి 2 డయాగనల్ లైన్స్, 1 హారిజాంటల్ లైన్. బి అంటే 1 వర్టికల్ లైన్ అండ్ 2 సెమీ సర్కిల్స్. సి ఈజ్ ఎ సెమీ సర్కిల్. అట్లా దే ఆర్ మేడప్ ఆఫ్ సింపుల్ ప్యాటర్న్స్, సింపుల్ షేప్స్. అదే తెలుగు తీసుకుంటే చాలా కష్టం, ఒత్తులు ఉంటాయి. అలాగే కు అంటే పక్కన ఇవున్నాయి కుడింతాలు, అలాగే పైన ఏత్వాలు ఉన్నాయి, కే కాయ్, అలాగే దీర్ఘాలు ఉన్నాయి, కీ. సో మొత్తం ముందు అక్షరాన్ని రికగ్నైజ్ చేయాలి, కాని దానికి కింద ఒత్తుంటే ఒత్తుకుని రికగ్నైజ్ చేయాలి, ఆ తర్వాత పైన గుడి ఉంటే గుడిని రికగ్నైజ్ చేయాలి, దానికి దీర్ఘాన్ని రికగ్నైజ్ చేయాలి, ఆ పక్కన అలాగే కు అలాంటివి ఉంటే అవి ఇట్లా 4 or 5 లెవెల్స్ మనం రికగ్నైజ్ చేయాలి. నా దగ్గర ఒక స్టూడెంట్, షీ హెస్ డన్ వెరీ గుడ్ వర్క్. తెలుగు హ్యాండ్ రిటన్ రికగ్నిషన్ ఆఫ్ తెలుగు రికగ్నిషన్. ఎవరు తెలుగులో రాసినా కంప్యూటర్ విల్ ఏబుల్ టు రికగ్నైజ్. మళ్ళీ తర్వాత దాంట్లో మళ్ళీ ఇంకా చాలా ప్రాబ్లమ్స్ ఉన్నాయి. కొంతమంది నిలబెట్టి రాస్తారు శుభ్రంగా, కొంతమంది పడుకోబెట్టి రాస్తారు, కొంతమంది అంటే ఈ రాసేటప్పుడు ఒకళ్ళ రాత ఇంకొకటి రాత సేమ్ గా ఉండదు కదా, రకరకాలుగా ఉంటుంది. అవన్నీ మనం కరెక్ట్ చేసుకోవాలి. సో ఇట్ ఈస్ ఎ బిగ్ రీసెర్చ్ ప్రాబ్లం. ఎనీహౌ ఇక్కడ జస్ట్ బీటెక్ స్టూడెంట్స్ కాబట్టి జస్ట్ ఐఎమ్ గివింగ్ ప్రింటెడ్ క్యారెక్టర్స్, నాట్ హ్యాండ్ రిటన్ క్యారెక్టర్స్, printed characters, and I am taking 0 to 9 digits. The same procedure for the for remaining letters also. So in commercial applications, where a better resolution is required, at least 16 to 16 bitmaps. So we are making standard bitmap 16 into 16. See this here. This is a 5 into 1, 2, 3, 4, 5, 6, 7, 8, 9. 5 into 9. Initially it is 5 into 9. 5 into 9 bitmap. Each digit is. Or you can convert it to 16 into 16. We must make it a standard size bitmap. So here, if we write 1 means, this is the shape of 1. That means pixel number 11, 7, 3, 8, 13, 18, 19 are in black color. Remaining are in white color. Similarly, 2 means 6, 2, 3, 4, and 10, 15, 20, 24, 28, 32, 37, 36, 41. Like that. So you can observe which pixels are being black color or which pixels are in white color. All these values of input pixels are given to gray level values. Gray level values of the input pixels are given to neural network. So number of neurons in the input layer is decided by the number of pixels in the bitmap. So here we have 5 into 9, total 45 pixels in the bitmap. It is a binary bitmap, that is 0 and 1. 0 represents black and 1 represents white, or otherwise vice versa. Normally 0 means black. This is the 1, 2, 3, 4 is the address or location, or neuron number. We can consider it as neuron number, input neuron number. But black means 0 and white means 1. And if it is bipolar, as we said, it is better to take bipolar. Black means -1 and white means 1. So since it is 5 into 9, the number of neurons are 45. If it is 16 into 16 is standard size, the number of neurons are 256. The output layer has 10 neurons. Why 10 neurons? We are going to write by only 10 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 0. So outputs are 10, input of 45, and the hidden neurons may be more than 45. As we say, 90 neurons. So complex patterns cannot be detected by a small number of hidden neurons. However, too many of them can dramatically increase the computation. So normally 19 hidden neurons, of course, the 90 is not at all a big size. But if you increase the number of hidden neurons, time increases. If you reduce the number of hidden neurons, you cannot identify the complex patterns. And also overfitting. If the number of hidden neurons are more, the overfitting. So, if the number of neurons is too big, the network might simply memorize all time. So this is 45 input neurons. Normally, hidden neurons must be more. As we said, it is more, it will definitely recognize the complex pattern. Here it is not a complex pattern, they are very simple patterns. That's why he has taken 5 input neurons to avoid the overfitting. So the inputs are nothing but 0 and 1. If it is a binary, it is a bipolar minus and 1. And outputs are 1 to 10. See here, we are getting only 1. See, that means it has recognized 2. So it depends upon training examples. 1000 test samples. And this is the learning curve also. We have shown learning curve, 3-layer neural networks. Sum of the squared error and epoch, number of epochs. See here, if there is only one hidden neuron, two hidden neurons, error is very large. 5 hidden neurons, error is decreasing. 10 hidden neurons and 20 hidden neurons. As we increase the number of hidden neurons, definitely error will be reduced and the number of epochs will take less. Convergence is high speed, but at the same time, we may have overfitting. So you must avoid that overfitting. And similarly, error, recognition error, 5 hidden neurons, 10 hidden neurons, and 20 hidden neurons. So try with the nice examples. As I have given only printed characters. So now with noise examples. Noise examples means handwritten. Then you come to know. So training the network trained with perfect example. This blue color is perfect recognition error. And with the noise examples. This is the noise level, as we are increasing noise level. Up to 0.2, they both are same. But if you are increasing noise, the network is able to recognize, more efficient. And another example, another case study is prediction. Predicting market value, share prices, or house rents, or house values, etc. So here the inputs are the house location, living area, number of bedrooms, number of bathrooms, land, number type of heating. Number of parameters are there when you are going to select a house for purchase or for rent. So you must define all these parameters. I also told in the area sessions, selecting a bridegroom. So similar here also to purchase a house at for a you will go for real estate agencies. Will ask all these parameters. Now the output is a well defined house. So an appropriate number of training examples can be estimated with the Windrow's rule of thumb, which suggests that for a good generalization we need to satisfy the following conditions. N is equal to NW by E. N is the number of training example, NW is the number of synaptic weights in the network, and E is the network error permitted and test. We can use this, how many number of parameters we can take. Number of weights by the error gives the number of inputs. Data can be divided into three main types: continuous, discrete, and categorical. Continuous data vary between two preset values, minimum and maximum, and can be mapped or messaged to range between 0 to 1. Message value max value minus minimum value, max value. And discrete data such as number of bedrooms, number of bathrooms, also they also have maximum and minimum values. So see here, I given some example for number of bedrooms. If there are no bedrooms means 0, if there are one bedroom means 0.25, two bedrooms means, this is mapping. This mapping must be carried out as I told in the previous examples. Mapping of the data is very, very important. So, some of the people who are working, who are doing research, they don't know this mapping. And they have completed their PhD. It is amazing. Without knowing transformation, without knowing mapping the data, they have completed the PhD. Simply they are purchasing, they are bringing the books and throwing on our face and getting the useless PhD degree. So this is the net we are showing, feed forward neural network, real estate appraisal. Location rating, mapping is given, location rating 7, depending upon post location or some far away from the city, we can give the rating, whether it is close to the city or something. Number of bedrooms, house condition, number of bathrooms, living area, size, land size, garage, type of heating system, AC machine. All these can be taken and the real values can be mapped into the, transformed into the new inputs of the neuron. And we are getting a response 0.3546, and again that is converted into its cost. Directly we can't get cost. Based upon the output response only, again we have some formula to calculate the cost. So to validate the results, we use set samples never seen by the network before training all the available data. A randomly defined training set test it, and once the training is completed, the network is able to generate. And also we can do benchmarking. You first of all try on the neural network, test it, validate it, and then go to practically the what is the cost of such a. Then you compare the price estimated by the neural network and the price actual price in the. If they both are same, almost are same, your work is good. The researchers are not doing the benchmark. So another class classification neural networks with competitive learning. Think about plant classification. Plant class based upon sepal length, sepal width, petal length, petal width. These are simple problems. Recently, I don't want to name a student. He brought classification of leaves and flowers like this, sepal length, petal length. It is a BTech project. Is it a PhD work? Of course, it can be done as a PhD work when you consider all the parameters and all the elements what I have discussed. What is the momentum? What is the learning rate? How many number of neurons must be there? How many number of hidden layers must be there? If all the parameters today what I have discussed, if we have implemented each and every point and we have done, then it is a perfect network to classify plant or leaf or flower. Then it will become a research. Without all these things, simply throwing and taking some input values like sepal length, sepal width, petal length, and petal width, and showing this is this particular flower, this is particular flower. What is that project? That project is nothing but a BTech student project. They are small students, but it cannot become a research project. Unfortunately, such type of research works also awarded PhD degrees. I am very sorry to say this. So anyhow, tomorrow sessions we will go to competitive learning, and we have another very important learning method that is uh, uh, feedback network. We have seen today feed forward networks. I hope you are aware very clear feed forward network, how to design a feed forward network, how to use the backpropagation algorithm, backpropagation learning, and some of the applications. Tomorrow we will see the feedback networks. Feedback networks, how to utilize, what are their applications, what are the parameters to be discussed. So now, sir, you can allow the students for their doubts.
Okay, sir. Dear participants, YouTube and Airmate, do you have any doubts? Please raise in chat box or raise your hand.
Sir, many students are asking for the feedback link. In YouTube, I have seen
Feedback
there.
link
Okay, no problem.
already YouTube and Airmate I will send
Uh,
it link. Send
okay.
that link.
If possible, if also send me feedback, that will be help me. Okay.
Okay, sir. Dear participants, do you
Yeah.
have any doubts? Please
Pawan
raise in
sir, Chief
chat box.
Executive Officer, Dennis Code. Sir, tell me your doubt.
Pawan ji, sir,
Uh,
please ask your doubts, sir.
nice meeting you, sir. Sir, that I am telling, sir, PhD work, a very good point. It is a research work. If the problem is small, you must do rigorous work. Normally, PhD work, sir, problem is very small and the work must be rigorous. There is no need to take big problems. There is no need to take big problems and simply pushing. That means the PhD work must not contain more number of objects. It must contain only one or two objects only. But they must be done rigorously with considering each and every element. As I told in this example, I don't want to name the name of the student. He has brought a PhD work, classification of leaves. Of course, it is a problem of BTech work only, BTech student. But anyhow, if you are doing that one, you must consider all the issues what I have discussed today. how many number of hidden neurons, optimal hidden neurons, hidden layers, what are the weights, what is the momentum, what is the learning rate. All these elements must be considered, discussed thoroughly. Then only it will become an optimal and good work to classify the leaves. No other work cannot be carried further to classify the leaves. But unfortunately, they are taking a simple problem and just pushing without doing any rigorous work. So take a small problem. Yeah, I have shown hidden neurons, predict hidden neurons. Normally, I have given the formula. Normally, hidden neurons will be more than that of the input neurons. But if you use more hidden neurons, again it goes for overfitting. That's why it comes in the empirically. When you are doing the experiment, you will come to know how many hidden neurons and hidden layers. So these are all the parameters. As I told in these slides also, all these parameters do not have any standard values. They must be predicted empirically. They must be predicted empirically. Sir, we need some insights about which architecture to be used on a particular application. Okay, definitely. I will explain tomorrow with some examples. Then we will be clear. Today I have shown a feed-forward architecture. I have shown the feed-forward architecture for pattern recognition application. Most of the pattern recognition applications will use feed-forward with backpropagation.
సార్ మన యూట్యూబ్ యూజర్ అడిగారు ఏఐకి డీప్ లెర్నింగ్ కి ఎంఎల్ కి డీప్ లెర్నింగ్ కి డిఫరెన్స్ ఏంటి?
అదే నేను చెప్తుంది, ఏఐ అనేది ఓన్లీ సర్చింగ్ టెక్నిక్. తెలివితేటలు ఇప్పుడు చెస్ ఆడుతున్నాడు. చెస్ అంటే కూడా అది ఆ తెలివితేటలు ఏంటంటే వెతకటమే, సొల్యూషన్ వెతకడం. రాజుగారిని ఆట కట్టించడానికి దారులు వెతుకుతున్నాం. అది ఏఐ. అలా కాకుండా ఆడంగా ఏమవుతుందంటే అడాప్ట్ అయిపోతాడు. అడాప్ట్ అంటే ఏంటంటే నెక్స్ట్ ఏమేయగలడు అపోనెంట్ నెక్స్ట్ ఏమేస్తాడు, మనం ఇది ఈ కాయ మూవ్ చేస్తే నెక్స్ట్ వాడికి వచ్చేస్తుంది. దట్ అడాప్టబిలిటీ నేచర్ భగవంతుడు మనకి ఇచ్చాడు, హ్యూమన్ బీయింగ్ మనకి ఇచ్చాడు, కానీ దాన్ని మనం వాడుకోవట్లేదు. దాన్ని సిక్స్త్ సెన్స్ అంటారు. జేమ్స్ బాండ్ సినిమాలో చూసాం. జేమ్స్ బాండ్కి సిక్స్త్ సెన్స్ ఉంటుంది. వాడు వెంటనే కనిపెట్టేస్తాడు, ఓ వీడా వాడా. అంటే మనం ఏంటంటే ఈ సబ్జెక్ట్ లో లీనమైతే ఆ సిక్స్త్ సెన్స్ వస్తుంది. కానీ రకరకాల ఇష్యూస్, సినిమాలు అవి ఇవి అన్నెసరీ ఇష్యూస్ అన్నిట్లు పెట్టుకోవడం వల్ల ఏంటంటే అడాప్టబిలిటీ పోతుంది, ఆ సిక్స్త్ సెన్స్ కూడా పోతుంది. ఆ అడాప్టబిలిటీ అనే ఒక ప్రాపర్టీని మనం మెషిన్స్ కి తీసుకురాగలిగితే అది మెషిన్ లెర్నింగ్ అండ్ జనరలైజేషన్ ఆల్సో. సో అడాప్టబిలిటీ, జనరలైజేషన్ పవర్ ఏఐకి లేదు, మెషిన్ లెర్నింగ్ ఉంది. ఇంకా డీప్ లెర్నింగ్ అంటే ఈ పవర్ రావాలి అంటే నెంబర్ ఆఫ్ హిడెన్ న్యూరాన్స్ ఇంకా డీప్ గా థింక్ చేయాలి. సో మెషిన్ లెర్నింగ్ లో నుంచి డీప్ లెర్నింగ్ అంటే ఏం లేదు, న్యూరల్ నెట్వర్క్స్ ని నెంబర్ ఆఫ్ హిడెన్ లేయర్స్ ఉపయోగించి మనం డీప్ లెర్నింగ్ ని డెవలప్ చేసాం. అదే నేను అడిగాను కదా మిమ్మల్ని, మీరు వాళ్ళు ఒప్పుకుంటే మీ హైయర్ అఫీషియల్స్, నెక్స్ట్ వీక్ ఐ విల్ టేక్ డీప్ లెర్నింగ్. అడిగారా మీరు? హలో
సార్ చెప్పండి సార్.
అదే మిమ్మల్ని అడిగాను కదా, మీరు వాళ్ళు ఒప్పుకుంటే నెక్స్ట్ వీక్ డీప్ లెర్నింగ్ ఎక్స్టెండ్ చేస్తాను.
సార్ ఒక్క నిమిషం సార్, నేను ఈ క్లాస్ అయిపోగానే ఒకసారి మీకు కాల్ చేసి మాట్లాడుతాను సార్.
అలాగే.
ఓకే సార్.
ఓకే, థ్యాంక్ యూ ఫర్ టుడే. థ్యాంక్ యూ. మే ఐ లీవ్? If any doubts are
okay,
there,
sir,
they can mail me. You can provide my mail address. They will mail. I will definitely help them.
Okay, sir.
In your Pavanji, I will help you in your research also. I think you are doing research on the CEO. He is doing research. I will help in your research. You can mail me also. We interested in learning. All are saying that they are interested in deep learning. Anyhow, let us talk with the higher officials. Definitely, he will help us. Okay. Thank you.
Okay, sir. Thank you.